So you can guide light with an optical fiber. And optical fibers that are small enough can support just a single spatial mode, corresponding to a ray of light that travels straight down the axis of the fiber. This is the kind of fiber that is used to transmit the internet, for example, where information is encoded on short pulses of light. Now our group has liked to use it for making lasers that emit very short pulses, and we've come up with a bunch of ways recently to make these lasers more and more powerful. If we keep increasing the energy we put into the fiber, eventually the pulse stops growing and it splits into smaller pulses, or it breaks up into noise. If we keep increasing the power because of the high intensity of light inside the fiber itself can also be destroyed. If we increase the fiber size, we should be able to send more information through the fiber, and we should be able to increase the power of fiber lasers. In these larger multimode fibers, light has more degrees of freedom in space. It has more spatial modes. In contrast to single-mode fiber, where light can only move in one space dimension, that is, right along the axis of the fiber, in multimode fibers, light is free to move in closer to 3 spatial dimensions. It can also move up and down, left and right, in a variety of complex paths as it propagates down the axis of the fiber. This makes the physics much more difficult. But in physics, difficulty and complexity can still be very beautiful, and the cascaded technological effects of big improvements to basic technologies like optical fiber transmission and fiber lasers will be pretty significant. These are things that would really affect everyone's daily life. So recently we've been trying to understand how intense pulses of light behave inside these larger multimode waveguides. One recent experiment we've done shows how beautiful the physics of this can be, and also how the different dimensions of light factor into its behavior in multimode fibers. So the experiment works like this. We have the laser here, and we can control the power using a half-wave plate and a polarization beam splitter. We couple the laser light into the multimode fiber, and we can control the field distribution inside the fiber by translating it relative to the lens with a 3-axis translation stage. Now typically when we couple light into the fiber and we look at what comes out of the fiber on the other end, we see a kind of messy beam, something that's a combination of many modes of the fiber. And generally this is not too useful for a lot of applications. But as we increase the power that goes into the fiber, the nonlinearity inside the fiber causes the light to actually self-organize. It goes from this messy beam into this nice round Gaussian beam that could be useful for many applications. As we increase the power, however, the beam blows up. It grows again. And this corresponds to the development of spectral sidebands that we can see on the spectrometer. So it's common to think of a beam of light as existing in and propagating through space. If we do that here, we expect the light to be very stable, and in fact most stable as that beautiful round Gaussian beam. But light is actually a spatiotemporal wave. It's 4-dimensional, and it always has degrees of freedom in time. As we see here, that can provide an instability for things we'd otherwise expect to be stable. In fact, it means that what seems like the most stable state of the system is actually the most unstable when you consider the full 4-dimensional spatiotemporal nature of light.